everyone. Today, in chapter Introduction to Analytical Chemistry, I am going to talk about limiting reagent and concentration of solution. Now, limiting reagent. When anybody is carrying out one chemical reaction, the reactants are not usually present in the exact stoichiometric amount, that is, in the proportion indicated by the balanced chemical equation. And the goal of a reaction is to produce maximum quantity of useful compound from the starting material or reactants. Frequently, a large excess of one reactant is supplied to ensure that more expensive reactant is completely converted into the desired product. The reactant which is present in lesser amount get consumed, and after some time no further reaction will not take place. Whatever be the leftover amount of the reactant, it would be present only. Hence, the reactant which get consumed limits the amount of product formed, which is also a desired product, and that particular reactant is called limiting reagent. Now consider the formation of NO2 gas from nitric oxide, which is NO, and oxygen gas. Initially, we used to supply 8 moles of NO and 7 moles of O2 gas. One way to determine which one of the two reactant is limiting reagent is to calculate the number of moles of nitrogen dioxide which would be obtained from the given concentration of nitric oxide and oxygen. But we see that limiting reagent will yield the smaller amount of the product. Starting with 8 mole of nitric oxide, we will find the number of moles of NO2 produced. If we take 8 mole of nitric oxide, we will get 8 mole of NO2, and we are starting with 7 mole of oxygen. So, because 8 moles of nitric oxide result in a smaller amount of NO2, NO must be the limiting reagent and O2 would be the excess reagent before reaction has been started. Now, concentration of solution. The concentration of solution is the amount of substance present in a given volume of solution, and it could be expressed in the following ways. We can determine mass percentage or weight percentage, that is W by W. We can determine concentration in terms of mole fraction. We can determine in terms of molarity and molality also. Now, mass percent. Mass percent is obtained by using this following formula, and the formula is mass percent is equal to mass of solute upon mass of solution multiplied by 100. Next is mole fraction. It is a ratio of number of moles of a particular component of a solution to the total number of moles of the solution. If a substance A is dissolved in substance B, their number of moles, suppose it is Na and Nb respectively, then the mole fraction of A would be number of moles of A upon total moles of solution, that is Na plus Nb. I can say here mole fraction of A is equal to Na, which is number of moles of A, upon total number of moles of solution, where A and B both are present, and I am taking Na as number of mole of A and Nb as number of mole of B. Similarly, if I want to find out mole fraction of B, then number of moles of B, that is Nb, upon total number of moles, that is Na plus Nb. Now, molarity. It is most widely used unit and is denoted by capital M. It is defined as the number of moles of solute present in 1 liter of solution. We can determine molarity by the formula number of moles of solute upon volume of solution in liters. Next is molality. It is defined as the number of moles of solute present in 1 kilogram of solvent. It is denoted by small m, and its formula is molality is equal to number of moles of solute upon mass of solvent in kilograms. It should be noted that molality of a solution does not change with temperature. Since mass remains unaffected with temperature, often in chemistry laboratory, a solution of desired concentration is prepared by diluting a solution of known higher concentration. The solution of higher concentration is also known as stock solution. Analytical chemistry also involves deducing some relation between two or more properties of matter. One of the classic examples is the relation between temperature and volume of a given amount of gas. A set of experimentally measured values of volume and temperature of definite mass of a gas upon plotting a graph paper appeared as you are seeing figure A. When points are directly connected, a zigzag pattern results. You are seeing in figure B. From this pattern, no meaningful results can be deduced. A zigzag pattern results due to the many type of errors which incur which incur in many measurements involved in experiment, which is C, which is actually B. Figure C shows a smooth curve which may be called as average curve passing through these passing through these points. In above example, it happens to be the straight line, and inference is V is directly proportional to T. While fitting to its smooth curve, care is taken the plotted points are evenly distributed. So, for each point, draw a perpendicular curve to the curve. The perpendicular represent deviation to the each point of curve, which you are seeing in figure D. The positive deviations are shown in red and the negative deviations are shown in blue. Take sum of all the red perpendiculars and all the blue perpendiculars separately. If the two sums are equal, or you can say nearly equal, the curve down shows the experimental points in the best possible representation.